I remember when I was in high school before I went to university. This is my introductory physics course. You can imagine me. I was a kid. I did not know what I wanted to do with my life, and at the time, I didn't not really care that much about physics. My physics professor was explaining what physics was and what physicists actually do. He showed us equations to drive the motion of particles. I thought that was kind of cool, but then he said that the physics could have much more complicated equations, and then he put on Maxwell's equations on the board. Of course, I did not know that there were Maxwell's equations. He just told us that these four equations describe electromagnetism. I was taking algebra at the time, and suddenly I was looking at what now I call the Big Four. I remember thinking, what does the triangle mean? What is that strange stretched out symbol? I think he showed us both the integral and differential form, which made the whole thing look even more incomprehensible. I'd never seen an integral sign before, and at the time I knew elementary functions, but I did not know calculus. So these symbols look like they belong to an entirely different language. Today I want to return to those equations, and I thought I understood them, and I kinda do, but there's still some genuinely beautiful physics hiding inside them. So let's unpack the big four. Before we talk about Maxwell's equations, we need to talk about electric charge. Um, we live on Earth, and Earth has a gravitational field that attracts us towards it. Newton's law of gravitation says that the force between two masses decreases with the square of the distance between them. Electric charges obey another inverse square law called Coulomb's law. The equations look similar, but electricity introduces something that gravity does not: repulsion. The idea was fascinating to me. The gravitational fields of the Earth, the Sun, and every ordinary mass I knew were about attractive, but electric forces can either pull objects together or push them apart. A positive charge repels another positive charge, a negative charge also repels another negative charge. That confused me at first because I had started thinking of negative charge as something that was inherently attractive, but negative does not mean attractive. The forces depend on signs of both charges. If Q1, Q2 is greater than 0, the charges have sign and repel. If Q1 and Q2 are less than 0, the charges have opposite signs and they attract. We defined the electric field as the force that positive charges would experience for a unit charge. The field points away from a positive source and towards a negative source. Put a positive charge and a negative charge together, and the field lines leave the positive charge. Curve through space, they enter the negative charge. This is an electric dipole. Now we need a way to turn that field line picture into mathematics. Field lines are used for drawings, but they are not little strings that we can count. To measure how much an electric field passes through a surface, we defined electric flux. Imagine enclosing a positive charge with a spherical detector surface. Break the surface into tiny patches. Each patch has an area vector dA pointing outward. The dot product EdA selects the components of the electric field passing normally through each patch, and summing of the entire enclosed surface gives the electric flux. For a point charge at the center of a sphere, the electric field radially outward and has a magnitude of ERQ over 4 pi epsilon r square. Every point on the sphere is the same distance from the charge, so the field has the same magnitude everywhere. The field is also parallel to every outward area vector. We can therefore take the field magnitude outside of the integral. The remaining integral is the area of the surface. The radius has disappeared. We can make the sphere larger or smaller, but the total flux will remain the same because the same enclosed charge is producing it. Therefore, the general statement is: this is Gauss' law for electricity, the first Maxwell equation in integral form. Now, let us make this equation local. The divergence theorem says that the flux of a vector field through a closed surface equals the volume integral of the divergence inside of that surface. The enclosed charge can also be written as the volume integral of the charge density rho, substituting both expressions that the Gauss's law gives. Both integrals are over the same volume. More importantly, the volume is arbitrary. We could draw it around any small region. If these volume integrals are equal for every possible volume, then their integrands must be equal by point. Therefore, the divergence of E is equal to rho over the permittivity of space. The integral form tells us about the local charge flux through a closed surface. The differential forms tells us what is happening locally. Electric charge density is the source of an electric field. This is Maxwell's first equation. When I was a kid, I remember playing with a bar magnet outside my house. I went into my dad's tool shed, found a bucket of nails, and decided that putting the magnet into it was a good idea. When I pulled the magnet out, the nails formed a long chain. It reminded me of those barrel of monkey toys where every piece hooks onto the next one. The reason is that the magnet aligns the magnetic domains inside of each ferromagnetic nail. Each nail becomes an induced magnetic dipole. Neighboring opposite poles attract, so the nails connect end to end. But what creates magnetism in the first place? A moving electric charge produces a magnetic field. For a positive charge, the direction is determined by cross product involving its velocity and the direction towards the observation point. This is why magnetic field directions are described with the right hand rule. Many moving charges form an electric current. The convectional current direction follows the motion that positive charges would have, even when the actual charge carriers are electrons moving in the opposite direction. The magnetic field circulates around the current carrying wire. Put two parallel wires beside each other, and something interesting happens. Currents in the same direction attract, currents in the opposite direction repel. This is different from the simple rule for stationary electric charges. Magnetic fields are axial vectors, and sometimes called pseudovectors, and their directions are governed by cross products. Now that we have a physical picture of magnetism, we could ask what magnetic fields do globally. Imagine a bar magnet with a north and south pole. Outside the magnet, the magnetic field lines leave the north pole and curve around into the south pole. Inside the magnet, they continue back toward the north pole, forming a closed loop. Now, enclose the entire magnet inside a closed surface, so magnetic field passes outward through the surface, but the same field eventually passes inward again. The total outward magnetic flux is therefore zero. This is different from the electric case. Electric field lines can begin on a positive charge and end on a negative charge. Magnetic field lines do not begin or end on an isolated magnetic charge in a classical sense. If we cut the magnet in half, we do not obtain one isolated north pole and one isolated south pole. We obtain two smaller magnets, and each piece still has both poles. Magnetic monopoles are possible in some theoretical models, but ordinary isolated magnetic charges have never been observed. Applying the divergence theorem gives, because the volume can be closed arbitrarily, the local equation is therefore the divergence of B is equal to zero. This is Gauss's law for magnetism, Maxwell's second equation. We could also see this result directly from the Via-Savart law. In its current density form, the magnetic field at an observation point r hat, or r vector, is an integral over the source point r prime. The cross product between the source current density and the r vector determines the magnetic field relationship, so B is perpendicular to both. Now, what I'm going to do is I'm going to keep the two positions separate, where my source variable will be denoted by prime coordinates so that the current is primed, and the observational variable or the probe variable as on prime coordinates so that the gradient acts there. And therefore, the cross of r prime with respect to the current is zero. Now take the divergence of B with respect to the on-prime observation coordinate r hat or r vector. The source current density takes on r prime, not r. Move the divergence inside the integral and apply the identity. The first term contains the curl with respect to r of j of r prime. That is zero because the current does not depend on the observation coordinate. The second term contains the curl of r prime over r cubed, but uh, r vector over r cubed is just equal to negative the gradient r over 1r, and the curl of the gradient is zero. Both terms vanish, so therefore the divergence of the magnetic field is equal to zero. The magnetic field has no local source or sink. Its field lines always form a closed loops. Suppose you have a bar magnet, a loop of copper wire, and an ammeter connected to the loop. While the magnet remains stationary, the ammeter reads zero. But as soon as you move the magnet to the loop, the needle deflects. The magnet never touches the copper, so what happened? Or what changed? The answer is magnetic flux. Magnetic flux measures how much magnetic field passes through an oriented surface. For a uniform field passing through a fat loop, this becomes. In this experiment, the loop and its area remain fixed. Moving the magnet changes the magnetic field passing through the loop, so the magnetic flux changes with time. The direction of the resulting current is determined by Lenz's law. Suppose the North Pole approaches the loop and increases the downward magnetic flux. The induced current creates its own magnetic field pointing outward, imposing a current. Viewed from above, the current travels counterclockwise. If the magnet moves away, the downward flux begins to decrease. The induced current reverses the direction and decreases the downward magnetic field, attempting to preserve the disappearing flux. The induced field opposes the change in magnetic flux, not necessarily the external field itself. The circulating electric field supplies energy to charges around the wire. The energy supply per unit charge around the circuit is called the electromotive force, or EMF. Faraday's law says is equal to the time derivative of the magnetic flux. The minus sign is Lenz's law. It records the direction of the induced response. Speed matters as well. Move the magnet slowly and the flux changes gradually, producing a small EMF. Move it quickly and the flux changes rapidly, producing a larger EMF. And for fixed resistance, a larger current. This is Faraday's Lenz's induction. Changing magnetic flux creates an electric field. Now let us write the statement more rigorously. Faraday's law in integral form is: by Stokes' theorem, the circulation of the electric field around the boundary equals the surface of the integral of its curl. For a fixed surface, the time derivative can move inside the magnetic flux integral. Combining both sides gives. Since the surface can be choosing arbitrarily, the integral itself must vanish. Therefore, the curl of the electric field is equal to the negative temporal component of the magnetic field. This is Maxwell's third equation. A changing magnetic field produces a curling electric field. I remember one of my professors demonstrating the force between parallel current carrying cables. When the currents flowed in the same direction, the cables attract. When one current was reversed, the cables repelled. Now imagine drawing a closed loop around several cables. Current coming out of the pages counts positively, while current going into the pages counts negatively. If the sign enclosed current is zero, the net magnetic circulation around the loop is zero. This does not mean the magnetic field is zero every point. It means that the closed line integral of the magnetic field vanishes. For an ideal infinitely long straight wire, a circular symmetry tells us that the magnetic field depends solely on only the distance from the wire. Along a circular path, a magnetic field B is constant in a magnitude and tangent to the path. The line integral therefore becomes. This gives us the right answer for symmetric straight wires. Now let us derive the general magnetostatics result from the Biot-Savart law. We're going to first define and then take the curl with respect to the observation coordinate r and move it inside the integral source. Use the identity. Because the current r prime does not depend on the unprime observation coordinate, two of the four terms vanish, and thus two surviving terms give. Inside the integral, the delta function selects the source point r hat equals r, producing the divergence of r hat over r cube is a three-dimensional Dirac delta function. One vector integral remains. We're going to call it k. To show that it vanishes, consider it's only its x component. Derivative with respect to x and x prime have opposite signs, so the gradient of f of x is equal to negative the gradient prime of f of x, and we're going to use the product rule in the prime coordinates. For a steady current, local charge conservation gives divergence of the current is zero. The divergence theorem then converts the remaining volume integral into a surface term. For a localized steady current distribution, J hat approaches zero on the boundary, taking infinitely far away. And of course, the same argument works for y and z components. So k hat is equal to zero, or k vector is equal to zero. Therefore, we have derived that the curl of the magnetic field is equal to the magnetic permittivity times the current density. Finally, we apply Stokes' theorem. The surface integral of the current density is the enclosed current, and thus we have Ampere's law for steady currents. Of course, from here, we could go the other way around. If we have the line integral, we could apply Stokes' theorem, and we get a double surface integral. We get two of them. We could take the curl inside, and we get the differential form of Ampere's law for steady current. At this point, we seem to have four equations. Charges create electric divergence, magnetic divergence is zero, a changing magnetic field creates electric circulation, and current creates magnetic circulation. Our job should be done, right? Not quite. Ampere's original law works for steady currents, but fails when charge density changes with time. To see what is missing, we need the continuity equation. Current density can be written as charge density times velocity. Now imagine a fixed volume in space. Charge can move through its closed boundary, but charge cannot simply appear or disappear. On each small surface patch, a current density times a dA element presents and selects the component of the current density passing through the boundary. Motion tangent to the surface contributes nothing to the flux. Integrating over the closed surface gives the net outward current. If positive charge flows outward, the amount of charge remaining inside the volume must decrease at the same rate. The enclosed charges. Conservation of charge therefore gives the minus sign appears because positive outward current decreases the charge inside. Apply the divergence theorem to the current flux density, and because the volume is fixed, the time derivative can be moved inside the charge integral. Since the volume is arbitrary, the integrand must vanish, and therefore the divergence of the current density has to be equal to negative the change in time of charge density. This is the continuity equation. It is the local mathematical statement that electric charge is conserved. Now let us return to Gauss's law for electricity. We're going to multiply by the permittivity of space to write the charge density as. Substitute this expression into the continuity equation. For smooth fields, the time derivative and the divergence must commute. Move everything to one side and collect the terms inside a single divergence. The new term is called the displacement current density. It is not ordinary charge physically flowing through a region. Instead, a changing electric field enters Ampere's law in the same mathematical position as the current source for the magnetic field. Therefore, Maxwell corrected Ampere's equation. Now the two curl equations have remarkable symmetry. A changing magnetic field creates a curling electric field. Current and changing electric field creates a curling magnetic field. These are the microscopic Maxwell equations in SI units. Now we can finally ask what they predict when there is no charge and current at all. Imagine being Maxwell. You now have four equations that unify electricity and magnetism. Naturally, you want to play around with them. Consider a region of empty space where there is no charge density and no current density. The relevant vacuum equations are. Now take the curl of Faraday's law, and then we're going to use this vector identity. But the divergence of the electric field is zero in a vacuum, so the gradient divergence term disappears. On the right side, substitute the vacuum Ampere Maxwell law for the curl of the magnetic field. Therefore, rearrange this into a standard wave equation form. The wave speed square is therefore that is the speed of light. Maxwell's equations do not merely describe electricity and magnetic effects, they predict that electric and magnetic disturbances can propagate through empty space as waves, and that those waves travel at the speed of light. Light is an electromagnetic wave. The equations also contain a fixed vacuum speed determined by the constants of empty space, rather than the motion of the source. The tension between this rule and the classical ideas about adding velocities helped Einstein motivate his special theory of relativity. Um, and now that we've run through the four equations, we could sort of see why they're so revered in all universities because Maxwell managed to unify what he thought were two distinct fields at the time, electricity and magnetism, and formed a new unified branch called electromagnetism, which is sort of the reason why unification is very important and very sought out in physics. Unifications could essentially lead to a grand theory of everything. We could only hope.